So we're going to remember Chung Park, and Don Carpenter is going to make some remarks after we watch the video.
Okay, this slide shows the plasmasphere in its two extreme states. The top one is the, I can't see it very well from here. The one at the top shows the quiet time plasmasphere in its puffed up state with the plasma pause at L equals 7. And the bottom one shows the storm time plasmasphere with the plasma pause at L equals 2. We have been, for some time now, concerned about the question of how the plasmasphere goes from one state to the other, and how this dynamic change in the plasmasphere may be related to what goes on in the underlying ionosphere. I think we have a pretty good understanding now of how the plasmasphere goes from this state to this state, how it recovers from the magnetic storm effects. We don't understand very well yet how the reverse process works. We have depended very heavily on our Whistler data from H station in Antarctic for this kind of study. Unfortunately, that station was closed in 1965, but since then we went back to that same area and established a new station at SIPO. And we just received the shipment of a large block of data, which I hope will help us answer the remaining questions. The recovery from this state to this state occurs by filling from the ionosphere. This depleted region here fills up from plasma flowing upward from the ionosphere on the day side. And then when the plasma rotates onto the night side, they're partially drained into the ionosphere to help maintain the nighttime ionosphere. But the draining on the night side is less than filling on the day side, so that there is a net increase in plasma content during the recovery process until the density level in the plasmasphere reaches a certain level where it just saturates and doesn't increase any further. I think the next slide illustrates this better. Let's just look at the top part first. This is deduced from Whistler's recorded at H station. I have plotted the tube content, plasma tube content here as a function of L value. And this curve shows the tube content profile after it had 1 day to recover from a magnetic storm. Then the second day, it recovers to this level, third day, fourth day, and on to the 8th day. And one thing you can notice right away is this apparent saturation level. So at any given point, the tube content keeps on increasing until it reaches this level. And at this level, the nighttime draining and the daytime filling balance each other out. So there is no further net increase. And there is a remarkably well-defined boundary separating the two regions. The inner plasmasphere, where this plasma is in a diurnal average sense in equilibrium with the ionosphere, and the outer plasmasphere, which is still filling up from the ionosphere. And notice that this demarcation line is at L equals 2.5 after 1 day of recovery, and it moves out to L equals 4 after 8 days of recovery. So it is a very slow process, and 8 days is a pretty long time in the life of the magnetosphere. There are bound to be some disturbances, substorm activities, which will tend to deplete the plasmasphere again and push this demarcation level further inward. So this demarcation between the inner and the outer plasmasphere appears to be more or less a permanent feature of the plasmasphere. The other process of how the plasma sphere gets depleted during disturbances is not well understood. We only know bits and pieces which have yet to be pieced together. I believe there are several processes involved in the depletion of the plasma sphere. One would be the peeling off of the plasma sphere by convection electric fields, which I'm sure Rick Chappell and perhaps also others will discuss later on in this at this conference. There is another important process, which is the dumping of the plasma into the underlying ionosphere. And these two processes may go on simultaneously at different local times. We don't know how this local time regime is carved up by these two different processes, but I believe the peeling off process probably works in the late afternoon local time sector, whereas the dumping into the ionosphere operates in the nighttime and morning, night and morning sector. I'll show you one example of this plasma dumping into the ionosphere. This one shows, this again comes from Whistler data. This is a tube content profile before a rather isolated substorm activity. Started out with this, and a few hours after a substorm activity, we had a profile looking like this. And all of this is inside the plasma pause. The plasma pause would be sitting farther out. L equals 5.5 or 6 perhaps. And from detailed analysis of the Whistler data, which I won't go into here, we could deduce that the process actually occurred this way. It started out with this initial profile, which was shoved inward by westward electric field. So you would have a profile looking as this dashed curve, but this was combined with a downward flow into the ionosphere, so the end result was this.
It's a real pleasure to talk about Chung. Unfortunately, he worked at Stanford for about 10 years, and then yes, Chung was a really brilliant student who'd only been at work at Stanford for a few years when he gave that talk, and it was obvious that he had done some very clever work, and I don't think anyone has ever duplicated his very astute measurements of the dumping of plasma into the ionosphere as part of the loss mechanism during the major erosion of the plasmasphere. So he really was very successful, not only as a modeler of the, or as an observer of the data, but also of an interpreter of the relationship to the ionosphere. He was one of the only magnetospheric people that I knew who was both an expert on the ionosphere and on the overlying region, which was really hard to come by in those days, but he went ahead and knew a lot about both regions. I first met him when I was visiting Byrd Station in 1966 in Antarctica. Had a delightful opportunity to meet him then, and yeah, well, this is here's from the meeting here. He made some major contributions in all sorts of ways involving the overlying region, including the effects of thundercloud electricity on the ionosphere and various subtle and important features involving the very low frequency wave propagation and catalytic effects in the magnetosphere. And this is just an example of the complex types of data that Chung worked with so effectively. It's a Whistler with multiple components at the top, which he had analyzed in terms of its various density quantities. And here's a plot with electron density on the left, log electron density versus radial distance, and these are just some 3,000 data points that he either scaled or arranged to have scaled very carefully to get the magnetospheric equatorial density profile. And here's an example of his thesis, and of course the great accomplishment he made straight off when he was first working was to demonstrate that the upward fluxes from the ionosphere into the overlying region were sufficient to explain the densities observed in the plasmasphere, and in particular sufficient to allow the nighttime ionosphere to exist as with a resource, the overlying region. And so he got into the question of this so-called diffusive barrier preventing the H+ ions from diffusing upward, and he went against or at least he provided the first definite results establishing those particular numbers. And in his thesis, he showed that there was sufficient fluxes of 2 to 4 times 10 to the 8th electron per centimeter squared per second upward into the high latitude plasmasphere, and this was really, in fact, this has really become gospel or routine now, and people don't even question the reality of this result. And here are some calculations he made of the daily recovery of the density, the total content along plasma field tubes versus day back in June of 1965. And this was these were his data points with a nice model of the increase in density, and then gradual recovery over an 8-day period. And then here is some of his comparisons of the ionosphere and plasmasphere, with the ionosphere below recovering within 3 days and the overlying region requiring longer, by at least 5 days or more, which was a nice early demonstration of the different physics that we're dealing with in the two media. And then he did some really astonishing work on so-called annual variation, or these are differences in electron density that occur at different, from December to June in the the meridian of the eastern US. And he also studied the development of irregularities in the ionosphere, the upward extension of thundercloud electricity, which might be explained, allow you to understand the development of a Whistler duct that would guide the energy between conjugate points. And then he also studied the precursor phenomenon, in which you have prior to the return arrival in the north of a strong 2-hop Whistler. Here in 2 cases we see preceding those Whistlers the elegant rising or complex rising tones, which are the so-called precursors, which defied and probably continue to defy thorough efforts to understand, but which he went a long way in discussing. So anyway, these are just a few of his parts of his legacy, which I continue to be. I'm still in awe of what he did, and I miss him greatly because he passed away some 12 or 14 years ago.